Hi, in the past couple of modules we've been talking about the multiple comparisons problem. So in the previous module we talked about controlling for the family-wise error rate. In this module we'll talk about controlling for the false discovery rate. So methods that control the family-wise error rate, such as Bonferroni, random field theory, and permutation tests, provide a strong control over the number of false positives that we will potentially observe. While this is appealing, the resulting thresholds are often quite conservative, and this leads to a test that suffers from low power. And of course, power is critical in fMRI application because the most interesting effects are usually at the edge of detection. So the false discovery rate is an alternative to the family-wise error rate, and it's a recent development in the multiple comparison problems literature, and it's due to Benjamin Hochberg, and it's from 1995. So while the family-wise error rate controls the probability of any false positives, the false discovery rate controls the proportion of false positives among all rejected tests. So before we start exploring this concept, let's start out with some notation. So let's suppose that we perform tests on M voxels. And then we can split the M tests into the following four boxes. We have voxels that are truly inactive and are declared inactive. There are U of those. Then there are voxels that are truly inactive but are declared active. There are V of those. Now there's also voxels that are truly active and declared inactive. There's T of those. And then there's voxels that are truly active and declared active. There are S of those. Really, we want our voxels to ideally be in the truly inactive declared inactive and the truly active declared active boxes, because then we've made the correct decisions. U, V, T, and S are all unobservable random variables. R here is an observable random variable, which is the total number of declared active voxels. So we know how many voxels, if we perform M tests, we know how many voxels that were declared active, and this number is R. However, we don't know how many of them were truly inactive and how many of them were truly active. Now, ideally, we want the proportion that was truly active to S over R, so to speak, to be close to 1, because then almost all the voxels that were declared active were truly active. V represents voxels that are truly inactive but were declared active. So these are what we call false positives. So we're interested in controlling V. So using this notation, the family-wise error rate is simply the probability that V is greater than or equal to 1. That's that we have one or more false positives. Using this notation also, we can write the false discovery rate as the expected value of V over R. So this is the expected number of false positive among all voxels that were declared active. Okay? And so this is an expectation. So the FDR is defined to be 0 if R is equal to 0. So if there's no tests that were declared active, well then there can be no false positives. A procedure controlling the false discovery rate ensures that on average the false discovery rate is no bigger than some pre-specified rate Q, which lies between 0 and 1, and which is specified by the researcher. However, for any given data set, the false discovery rate need not be below this bound. So we're just saying that on average, in expectation, it's being controlled. But for any given data set, it can be above or below that value, Q. So any FDR controlling technique guarantees control of the FDR in the sense that in expectation, this ratio V over R is going to be less than or equal to Q. So a classic procedure for controlling the false discovery rate is the so-called Benjamini-Hochberg procedure. And it's pretty simple to perform. So basically the first thing we do is we select a desired limit Q on the false discovery rate, say 0.05. Here we say that out of all the voxels that are declared active, we want to limit the number of false positives among them to just be 5%. So we want 95% of them to be truly active and only 5% on average to be false positives. So once we've chosen that, the next thing we do is we take all M p-values, so we have one p-value corresponding to each test, and we rank them from smallest to largest. So p parentheses 1 is the smallest p-value, p parentheses 2 is the next smallest, all the way up to p parentheses m, which is the largest p-value. and we plot them in order. Next, we draw a line I over m times q, where I is the rank of the p-values, and we let r be the largest I such that p of I is less than or lies below this line. Then we use this as our rule, and we reject all hypotheses corresponding to p1 up to pr, and those are the voxels that are deemed active. Now, if all null hypotheses are true, the false discovery rate is going to be equivalent to the family-wise error rate. However, any procedure that controls the family-wise error rate will also control the false discovery rate. So a procedure that controls the false discovery rate, such as the Benjamini-Hochberg, can only be less stringent and lead to a gain in power. So the thresholds are always going to be a bit lower using false discovery rate than with family-wise error rate. And so there you're going to get a little bit more power because of that. And so since false discovery rate controlling procedures work only on the p-values, you don't really actually need the actual test statistics, and it can be applied to any valid statistical test. So we just need to have the p-values and not the actual test statistics here. Okay, so that's a brief introduction to the false discovery rate. It allows us to control the proportion of false positives among all rejected tests. In the next module, we'll compare the family-wise error rate and false detection rate a little bit more. Okay, I'll see you then.